So uh, basically we know that in the last century the planet has warmed by about, global mean has increased about 0.85 degrees, now 0.9 degrees. And India also, the temperatures have increased by similar magnitudes with more accelerated warming in the last 2-3 decades. And so the attribution in the last report and also in the fourth assessment report, it's very clearly emerging that the recent increasing trend what we have witnessed in the last few decades globally and also on various continental scale is due to the influence of increasing greenhouse gases in the atmosphere. And so to study this climate change, of course when you come to regional levels like the monsoon, there are a lot of uncertainties about the impacts of this increasing temperatures. And yesterday's talk by Annamalai and others, they pointed out the problem with the CMIP-5 models, even for the present day climate, how realistic they are in simulating the rainfall over India. I think there is all the models are spread all over when you compare with the observations. So this is a big concern, how to improve the models and how to understand the processes both globally as well as regionally. And this was our basic philosophy. And so to the science of climate change at our center in IITM is mainly to focus on the science of detection, attribution and future projections of global climate and the regional climate, including the monsoons, variability and change. And our roadmap for this started sometime in 2010-11, that you develop an Earth system model. You start with a good coupled model, atmosphere-ocean coupled model, which has a good mean state, a realistic mean state. It has a good fidelity in capturing the global as well as the monsoon climate. And once you have such a model, and it also has a realistic representation of the intraannual variability of the monsoon and various components of the features of the ocean atmosphere coupled interactions. And once you have such a modeling framework, then you can include various components of the ESM like biogeochemistry, interactive CIs, aerosol chemistry, transport and so on. So with this philosophy we started, and at that time there was this monsoon mission. There was agreement between NOAA and IITM for improving the monsoon forecast using the CFS model. And the model was there in 2011. And the forecasting groups at IITM, the seasonal and the extended range groups, they started working on this model and made various improvements to improve the skill of the seasonal forecasts and also the active and break spells. And so at that time we thought, why not develop a Earth system model based on the CFS. So at that time we basically started with the CFS V2 with the T126 resolution, that's about 110 kilometer grid space with 64 vertical levels, and it has the simplified Arakawa-Schubert scheme, the original, and various other parameterization schemes, physical processes. It has an interactive ocean model MOM4, which was the previous version, with half a degree poleward of 10 degree latitude, and near the equator it is about 0.25, and with 40 vertical levels and interactive CIs. So this was the framework. And then when we saw this model, one of the problems this model had was a very strong cold SST bias, and that was one of the big concerns. And so to go for climate, and it was basically a seasonal forecast model and not really a long-term model meant for studying long-term climate. So there was a big cold SST bias. And so when we start the model, let us say from 2009 or 10 initial conditions, and then you run in the first 20-30 years, it would go into some other climate, it would cool drastically. And this was a big, and that cooling would persist for several decades and maybe even up to more than a century. And of course the model itself, the dry bias was there over the Indian monsoon in the CFS V2, and this is the IMD rainfall. So the question is, how do we make a start? So we said that probably first thing we should do is replace this MOM4 with a newer version. At that time the MOM4 P1, which had better ocean physics, ocean mixing, ocean processes, and it also came with the interactive biogeochemistry. So our colleagues spent a lot of time just replacing the ocean component of CFS, MOM4 P0 by P1. This was the first step that happened. That itself took quite some time. And so initial model we had was at T126. So from the CFS we moved to T126 ESM version 1. Only the change is replace the MOM4 P0 by P1, and we could run complete integration for more than 100 years, and then this was first published in BAMS. We reported that, and so you can see that initially the CFS used to have this cold bias, and when we included the new MOM4 P1, this was an in-house development at IITM at our CCCR. This brought down the bias by almost global mean SST surface temperature by 0.8 degrees, and this was the first encouraging step. And but then this model still had huge bias in terms of radiation balance at the top of the atmosphere, more than 6.5 watts per meter squared. So clearly it was not ready to be a climate model for making climate projections. And so this drift, which most of the models, even when you look at the GFDL CM2 or CM2.1, in the first few years, these are basically the differences with observations when you do a free run of the model. Much of the heat will go into the deeper layers, so there would be warming as the integration proceeds, and whereas at the surface there would be more cooling. And you can see that CM2.1 that improves, the subsurface warming was significantly improved with the newer version, and the same thing we see between ESM 1 and CFSV2. Still the cold bias is there, I'm not saying that, but the warming that used to, all the biases penetrating into the deeper layers was reduced, and this was one of the main reason for reduction in the global mean SST. And when we looked at when you look at the precipitation in the CFS2, and this is the ESM first version of the model, some of the excessive precipitation over the Western Pacific, that was somewhat reduced, but the dry bias over India, we did not make a big improvement. Still the dry bias continued over the central and northern parts of India. But interestingly, the first version of the ESM showed a good ENSO variability. When you look at the intraannual variation of the sea surface temperature, it was more extending into the central Pacific, whereas in the previous version, the largest variations were mostly confined in the eastern equatorial Pacific. So some improvements in the ENSO simulation, but when you look at the monsoon precipitation over India, there wasn't much in the seasonal cycle of rainfall over India when you compare with observations. There was not much of improvement in the ESM version 1. But due to improvements in the temperature, the NINO 3 SSTs were improved, the seasonal cycle, as well as the ENSO monsoon correlations were slightly better captured compared to the CFS version 1. And we also looked at various other modes of variability like the Pacific decadal oscillation, as well as the ENSO, which are standing out nicely in the ESM 1 compared to the CFS 2. So this was a background, and this happened sometime in 2013-14. But as I said, there was a huge radiation bias, and so in the last 2-3 years, we have mainly focused how to improve on the radiation bias. Now the latest version shows this is the TOA flux at the top of the atmosphere. This is up to 300-year run, various improvements have gone, and now the radiation imbalance is about 0.7, 0.8 watts per meter squared at the top of the atmosphere. And this model has now, latest is it has run up to more than, this is a pre-industrial run with all the pre-industrial values of the greenhouse gases, aerosols, and other land cover changes. So the model has somewhat stabilized. We'll be extending it to a few more centuries, and the air temperature is also kind of stabilizing, as well as the sea surface temperature, and there is a good radiation balance between the incoming and the outgoing radiation at the top of the atmosphere. And these developments in getting a radiatively balanced coupled framework, we also find this has happened largely because in the version 1, there were a lot of the way the fluxes were exchanged among the different components between the fluxes were computed, especially in the ice-covered areas, both by the GFS model and the MOM4 P1, and that was creating a lot of problems in the inconsistencies in the way fluxes were exchanged. And that we have now identified that problem, and now presently the flux computations are in the oceanic regions are only made by the MOM4 P1, and we are allowing that to interact. And there was also a partial grid implementation for computing the fluxes and their exchanges around different components. Earlier, especially in the areas where the ocean and the land used to be there, so assigning it used to be as the grid used to be assigned either as a land or a ocean. Now there is a partial grid implementation. This is one more big development that has happened, and because of these improvements in the fluxes, and there's also, I'll come to the next slide, the sea ice distribution in the polar regions have improved. Earlier there used to be excessive freshening of the North Atlantic, and that used to weaken the thermohaline circulation. I will come to that. So the Atlantic overturning circulations have improved, and that has improved in this model, and also the equatorial heat transport or in the model has improved. Also, we have improved the monsoon, and overall general circulation of the atmosphere has improved. I'll come to each of these things. And in addition to this correcting these fluxes, one of our young colleagues, Mr. Prajesh, he visited NCEP. At that time, one of the issues for addressing the energy imbalance was the work done by Brotherton et al., where basically this energy that is input into the net downward shortwave flux, it goes to both the generation of the internal energy of the system as well as the kinetic energy of the winds. But the dissipation effects, frictional effects of the winds can also feed back to the internal energy, and that was missing in the GFS. So this scheme had already, it was in place in NCEP, and Prajesh managed to get it in our ESM, and that also contributed to bringing down the radiation imbalance by almost by 3 watts per meter squared. And so presently we have a system where the radiation imbalance is close to 0.5 watts per meter squared at the top of the atmosphere, and it is at par with most of the state-of-the-art CMIP-5 models that we see. And so this is a paper that I picked from Lucarini, where they have looked at, so this is the pre-industrial run where from the GFDL ESM2, I think GFDL 2.1, where the imbalance is, I think, slightly less than 0.5 watts per meter squared. So, and so of course spatially global mean we are okay, but regionally when you look at the satellite observations, this is of course for the present day, the satellite era, and this is the pre-industrial simulation. Spatially of course there are differences, but the global mean balance is there, and the top of the atmosphere. So this is a net summary. With the present version, the version 1 with a T126, the imbalance at the top was about 6.6 watt per meter squared. We have brought it down to almost 0.8, and at the surface is also a similar 0.75. So the atmospheric absorption is very low, something like 0.05, which is in a pretty good state. And one more thing I want to remind, the ESM version 2, which we have developed more recently in the recent years, it is at a lower resolution, T62, because this testing and validation at high resolution was it was taking much more time, and so it was not practically possible. So we adopted a T62 resolution, much coarser, about 180-190 kilometer grid. And so other thing is we have also improved the monsoon precipitation over India with a lower resolution because of a new convection scheme, which Partha et al. They wrote a paper using the Han and Pan convection scheme. So we replaced the old SAS scheme by this new SAS scheme, which incidentally improves the rainfall over the central India. So because we are focusing on the monsoon. So the mean monsoon rainfall, even at a coarser resolution, the dry bias has significantly improved in this new version. And basically this is because of the new convection scheme, Hannan-Pans convection scheme, which was introduced, and they had basically problems in representing the stratocumulus clouds in the eastern Pacific. So keeping that in mind, they had developed a scheme because the previous version of SAS had only entrainment happening at the lower level and outflows just at the top. But this, it has at intermediate levels also, you have entrainment affair, and this is more physically consistent scheme. And Partha et al., they had published a paper on this new impact SAS scheme on the monsoon rainfall, and they showed that, they noted that in the CFS 126 with the new SAS scheme, the rainfall over this central and eastern part significantly improved compared to the previous CFS. So this was the motivation. We said that we should use a new convection scheme for the monsoon, and that has gone into the ESM. So as you can see, the lower resolution ESM has a better rainfall over the Indian land region, and as well as some of the biases in the West Pacific has also mitigated, but still model still has its own problems. It says still the dry bias continues over India. And we also looked at some of the general circulation features from this 300-year run of the ESM2 and the previous version. One of the important things is this is the 850 millibar wind and geopotential height. This is during the June, July, August, September months. We see the summer monsoon cross equatorial flow. And interestingly, one of the big improvements in the subtropical anticyclone, Pacific anticyclone, is relatively stronger in the ESM2. This is a comparison with the ERA interim as compared to the previous version. And also the easterly trades in the Pacific have significantly improved. And when you look at the pressures over the ocean, southern subtropical Indian Ocean and southern Indian Ocean, they were somewhat kind of weaker geopotentials heights as compared to the previous. So looks like the pressure gradient, we have not plotted the surface sea level pressure gradients, they are also improved. And this basically sets up a large scale cross equatorial flow. There's an improvement in this. So largely because of the bias improvement in the biases and the fluxes which we have improved appears to be influencing these low level fields. But when you look at the upper level 200, because in the summer monsoon time you have a very organized convection, and in the upper level we have this anticyclone known as the Tibetan anticyclone with strong easterly jet, tropical easterly jet, and you have a warm troposphere, upper and middle and upper troposphere. That aspect is still weakening. The outflows at the divergent outflows at the upper level are still not so prominently, they have not improved compared in the ESM version 1. So still that problem is there, and this we have seen even for the winter time. So winter time also we see that improvements in because we have the seasonal reversals of the winds. You have the Siberian high and the northeasterly winds coming from the Asian continent, and those seasonal reversals are seen. But more interestingly, the subtropical anticyclones are especially both in the Indian Ocean and the Pacific Ocean, the winter time are much better captured in the new ESM1, ESM V2. And whereas the upper level divergent circulations associated with the Walker circulation or in the Indian Ocean east-west circulations, they have not still there. They don't show major improvements as compared to the version 1. And we also had, because as the MOM4P1 ocean model also comes with a interactive biogeochemistry, so it is known as a topaz model, where the ocean circulation and also the biogeochemical parameters are continuously interactive. And this is important for the monsoon region because of the seasonal reversals of the winds. During the summer monsoon time, because of the strong monsoon wind, you have upwelling off the coast of Somalia and also in the Arabian Sea, which brings a lot of nutrients and this ocean color to the top. And this is a simulation by the MOM4P1 because of associated with this increased upwelling of cold waters and more productively rich waters. And having this in the model is very important. And also it's also important to look at this because in the Eastern Pacific, as many of you know, this is a source of region of upwelling, and so as with ENSO variations like strong La Nina events can increase the ocean color like 98 La Nina, whereas when you have suppressed upwelling during El Nino periods, the ocean color. So from the satellite data, you can validate these simulations from the CWIFs. And so this is from the, so in our ESM V2, we are also switching on the biogeochemistry, although it's very, very expensive because in terms of memory and also in terms of computation. So this is from the ESM V2, the latest 300-year simulation, the summertime upwelling of the Somali coast. Of course, it's kind of more exaggerated when you compare with the observations. And also in the Eastern Pacific, as I told you, very extended ocean color associated with the strong trade winds, the easterly trades, which is increasing the upwelling of the east coast of the west coast of South America. And so one of the reasons for the improvement in the monsoon, as I said, the cross-equatorial flow has improved because of the changes in the surface pressure patterns and also in the geopotential heights. But more interestingly, we also find that yesterday Annamalai was talking about this moist static energy. So when we look at the moist static energy field over the from the ERA interim and the ESM V1 and the ESM V2, you can see that higher moist static energy extending even into the Indian land region, and the gradients in the moist static energy are much more prominent in this model as compared to the ESM V1. The moist static energy meridional gradients are much, much weaker. And this improvement in the moist static energy comes because of when you look, this is a section of the specific humidity which you have taken over the Indo-Gangetic plain, or a section from, I think it's from 60 east to 110, 100 degree east. You can see the humidity in the ERA interim extending even up to 600, 700 millibar, whereas in the ESM1, the humidity was mostly confined to the very, very close to 859, 900 millibars or so. The ESM1 V2 is clearly taking the humidity up into the upper layers. So these are all some of these again probably the effect of the new convection scheme. And when we look at the precipitation seasonal cycle averaged over the Indian longitude 70 east to 90 east, this is the latitudinal variation latitude, and this is the month by month axis. This is from the observations. You can see that during the summer monsoon time, the rainfall, the ITCZ is located primarily to the north of 15 degree north, whereas the equatorial Indian Ocean is devoid of convection to a large extent on a monthly scale. But the ESM version 1, the northward movement of the rain was more limited, whereas you had more rainfall happening near the equatorial latitudes. And this equatorial bias in the equatorial precipitation has been reduced in the seasonal cycle in the ESM version 2, and this rainfall over the Indian region is extending more northward. So these are all some of the positive signals. And when you look at make a Taylor diagram, this is over of rainfall showing the standard deviations, and this is over a larger region of the Asian monsoon. A large number of models, they seem to be doing well, but when you look at just over the Indian region, only a handful of models are there. Although because of the low resolution, the variability is somewhat underestimated, but it is much better compared to models, outliers which have very, very high standard deviations. And we also looked at the seasonal variability of Nino 3.4. In the version 1, the El Ninos used to extend even beyond the winter season. This was a big one of the issues. And this is from the observations, the black line, and the blue line is from the ESM V2. Although it seems to there is a change, it decreases, the variability decreases, but it's somewhat much more kind of exaggerated compared to the observations. But the El Ninos are not really extending far into the next year. And when we look at the ENSO monsoon teleconnections, we just looked at ESM V2 compared with many other models which were inside that circle which I had shown in the Taylor diagram. The timing of the ENSO monsoon correlation it's matching with the observations, the peak correlations when they happen. So some of these signals are very, very promising, the large-scale teleconnections. And we also looked at the, when you look at the teleconnection of the monsoon and the ENSO, that basically the Nino 3.4 and JJ's precipitation from the observations. So that both the ESM 1 and 2 are capturing by and large. There are some differences. But over the Indian Ocean, I think the link with the Eastern Indian Ocean, SST, and the teleconnections over the northern parts of India, so that is much more brought out prominently in the ESM V2 compared to the ESM V1. And so we also looked at some of the aspects of SST variability in the Indian Ocean, the first two EOFs, and if you see basically in the ESM V1, we had more of this SST warming. This is associated with a very deeper thermocline in the Eastern Indian Ocean. That problem has been mitigated by and large associated with this ESM V2. This is part of the second EOF pattern associated with the IOD-like pattern. And the ESM V1, we are having more warming in the Western Indian Ocean. So one of the implication could be the new ESM V2 could be producing more IODs because of this. This is our feeling. And the other thing is, because as I said, by improving the fluxes in the polar regions, we improved the sea ice distribution. This was one of the big, especially during the JJA season. This is from the observations from the Hadley Center sea ice, and this is the ESM V2. In the V1, it was the sea ice in the northern hemisphere was very much underestimated, and also in the summer hemisphere, even in the southern hemisphere also, this problem was there. So this problem has been very much improving, and one of the consequences was to improve the thermohaline circulation now, which is very important because of the sinking of the cold and salty water in the northern Atlantic, and also the flow of warm waters at the surface associated with the Gulf Stream and so on. This is very important, one of the important climate drivers when we are looking at long-term climate variability. This was the problem when you look at the salinity in the Atlantic. This is from the World Ocean Atlas. This is the V1. You can see a very, very large freshening of salinity in the North Atlantic, and that we have reduced because of the improvements in the fluxes. And because of the improved salinity distribution, one of the consequences, this overturning circulation, this is basically a plot of the stream function, this from the GODAS, and this is the version V1. Even CFS, this is a big problem. The overturning circulations were very, very weak, and this has significantly improved. And when even the bottom waters, what we are seeing at the subsurface, once we run the model for another few centuries, this will also develop. And presently the maximum transport is something like about volume transport is about 17 or 18 Sverdrups, and there are some observations in recent times by the rapid array. And so this is one of the other development that happened was we tried to include the aerosol. This has taken some time because the CFS model comes with a climatological aerosols, prescribed climatological aerosols, which interacts with it's a single moment scheme. It interacts only with the radiation transfer code. There is no indirect effect. First we started working with the aerosol concentrations provided by the CMIP-5 for the different species like dust and black carbon and organic carbons. These are all for various time periods. We tried to understand. One of our colleagues, Ayantika, she is working on this, trying to incorporate. And she used to calculate from these atmospheric concentrations for different species. We did all these computations of this aerosol optical properties, which was done like the AODs and the single scattering albedo and the asymmetry parameter, and these were then input into the ESM for the RRT radiation code. And and we used to compare, validate with the CESM simulation and make a comparison whether it's working or not. And but subsequently now IPCC for the CMIP-6, they are giving the optical aerosol optical properties directly, the AODs and the asymmetry parameter. This is basically coming from the Max Planck group, and So they are giving both for the natural aerosols. So the pre-industrial aerosols at the time of 1850 is mostly natural aerosols. And what they have done is they use a scheme known as the MAC V2, which is basically giving the background natural aerosols. And in the future, they give the fine mode aerosols for the anthropogenic aerosols based on a plume model. And so this was a test experiment where we did a switch on, switch off experiment. One experiment where we switched off the aerosol, and the other one just have the natural background aerosols, basically the dust and the sea salt, and 250-year runs just to make sure whether we are doing the aerosols correctly. So what we found was the aerosol radiative forcing in clear sky was about close to minus 2.5 watts per meter squared at the surface. And this change in the surface temperature, global mean temperature, was about, the decrease in the global mean temperature due to the aerosol was about 0.53 minus 0.53. And we also saw some precipitation changes, but this was just a sensitivity type of experiment. And now we also did a 250-year run just to examine the kind of for the 2005 aerosol observations. We have both the satellite observations as well as the model-based calculations. And this is a reconstruction going back to 1850. And when you do this difference, this is the AOD in at the 550 nanometer, and this is an example of the precipitation change. We do see some changes in the rainfall, but we have to do further analysis. And also we have included the land use land cover changes, which is basically known as the harmonized data set coming from Hurt et al. And this has been from the pre-industrial to the 20th century, and it is extended as a continuum into the future. And so it tells you how the land covered, the forested areas have been replaced by agricultural lands and so on. So the reconstruction is all, details are described in the CMIP data sets. So depending on we have calibrated the CMIP data set depending on the different vegetation types that are available. There are about 13 vegetation types for our model, which we have given, and this has also been tested. So what we have now is all these different forcing elements for climate studies. We have a radiatively balanced system, SST biases are improved. The monsoon rainfall over India has improved compared to the previous, although it's a low resolution model. And we have also now, this is IITM ESM will be contributing, this is the first model from India that will be contributing to the CMIP 6 and the IPCC assessment process. And we have just basically will be doing the basic experiments known as the DEC because of the, we did not commit to other things. Maybe we'll be doing the global monsoon MIP and some of the MIP experiment, but at the moment we just want to focus on the main DEC experiment. And we have committed to doing these 5 mandatory experiments for any entry-level model, and we have to make this multi-year pre-industrial run is going on. This we have to start once this is done, and then instantaneous CO2, and then a historical experiment where this land use aerosols and all have to go. So this is all targeted in the next couple of years. So in summary, what I want to say is the first version of the IITM ESM2 was developed at the Center for Climate Change Research in IITM by incorporating the MOM4P1 with biogeochemistry. And after that, some of the improvements that we saw was the reduction in the cold SST biases. The ENSO and PDO are very robust and spatially more coherent. ENSO monsoon teleconnections are well captured. And this was basically, this was the first step in transforming a seasonal prediction model to a climate model, which was published. And over the last couple of years, we have made improvements such as reducing the major improvements like reducing the imbalance in the radiation, improving the mean monsoon rainfall, improving the sea ice distribution, improving the Atlantic overturning circulation, the biogeochemistry, and the time varying aerosol properties have been included. And we are also trying to improve the hydrological balance because of the discharge from various land points into the ocean, river discharges, and we'll be contributing to the IPCC 6th assessment report. The future roadmap. So in addition to doing these experiments for the CMIP 6, we also want to address basic science questions on the detection, attribution, and future projections using the IITM ESM, both the global phenomena as well as regional climate change, including the monsoons. And in the next 2-3 years, they also want, because the resolution was very coarse, T62, it's because many people for application study, they want the model inputs, whether hydrology model or agriculture model and so on, crop modeling, at higher resolution. So our immediate plan is in the next, until next 3-4 years, we want to focus on a high resolution global model, only the atmospheric version of the IITM ESM for dynamical downscaling. And this is our timeline, 2018 to 2021. And we also plan to have a high resolution IITM ESM fully coupled model. This is the plan by the ministry. This will go until 2025, just for the next 15-year vision. So I have put 2020 to 2025 plus. At the moment, given our computational resources, the ocean resolution, this is at a 27-kilometer atmosphere model. The ocean, we have kept a moderate resolution at the moment. This will again depend on what kind of computer development happens, infrastructure availability. And but in the timeline, we also want to have a next generation ESM, because most of the processes like aerosols or chemistry or carbon cycle, they are all prescribed. So we want to have a next generation ESM, which much more interactive components. That's also a kind of a extended plan. So with this, I just want to end my talk. Thank you.
Thank you. You have very good model now.
Thank you.
Questions?
Yeah, I was going to say the same thing. It's very impressive,
Thank
but
you.
just among friends. I mean, you didn't make anything worse. Everything was better.
Yeah, yeah, because we have not seen many things. See, once we start seeing, we'll see what are the limitations with the once we.
That's anyway. I mean, that was just a humorous comments, because normally we get both. But
Yeah.
this was very impressive. Are you planning to make any seasonal predictions using this latest version? Have you done any? Just for an example.
No, sir. We have that we have not yet done. That maybe that is we have to. We
It
have to
will
see
be
that.
extremely good idea, especially because I saw some of your biases were so much better than most of the seasonal prediction models. At least a few cases, just to get an idea. It will be extremely useful.
Okay.
And that's the sort of bring certain amount of seamlessness. Very
Okay, sir. Thank you.
We exam MJO.
MJO, I have we didn't look into it. We looked at other things. MJO, we have not seen.
I'll second what Professor Shukla said. Very impressive. It's a very, very nice and sophisticated overview of the diagnostic, so I commend you on that. I was curious about the precipitation improvement. So you changed the convective scheme to get better. It's basically the endogenetic plane is where the problems are in the summertime monsoon precipitation. I'm wondering, because by the time you got to that, I couldn't look back at the other precipitation figures. Did that help or change the precipitation over other land regions? I mean, does that affect the Amazon or something like that?
Maybe there's a global map. I'll just put it. Yeah, there are still biases. Even over India, there is an improvement, but still the dry bias is continuing.
Yeah, you had a global map of precipitation.
Yes. I think over Africa, when you compare the trim, so probably we are underestimating some of this
So it
Rahel.
it got lower elsewhere,
It
right?
is, yeah. So
Overland.
it is lowering here.
Yeah, the Amazon's really Amazon got drier.
Yes,
And
Amazon
Africa
is
got
drier.
drier, which is interesting.
Yeah.
Please.
Very impressive. So this is good for me to see all these diagnostics in one place, ocean and everything. So I'm just curious. So there is also an improvement of sea ice. I'm just, so is this just a consequence of the improved ocean circulation, or is this a different sea ice modeling there, like, or different resolution sea ice?
No, the CI's model is the same. I mean, the same model. We didn't change the model. I think originally CFS as well as the ESM, the way the fluxes were exchanged were not proper, and because some of the when you look at ESM1, the flux computations were done both, especially in both by the GFS as well as the MOM4 P1, from the ocean model, and the way they were exchanged were not consistent. This used to create a lot of problems. I think this problem, was identified. This was one of the big issues, and now we decided that fluxes, whatever is computed by only the ocean component, will be allowed to interact. So that is it's a change, and also the way the grids are defined at the boundaries. Also, we have changed the partial grid implementation. So the fluxes at the surface, I think that improving the fluxes at the flux exchange is one of the effects I see in terms of improving the anticyclones and so on, when you subtropical anticyclones. But still the problem when you go to the upper level, you don't see in terms of the divergent circulations. So still the convection, it's definitely a better convection for the monsoon as far as we are concerned. But still there is scope for further improvement. That's how I would put. Yeah, not here, sorry. Yeah.
Jim.
So everybody said very impressive, I'll say it too. But the question about the sea ice,
Sorry.
and yeah, sorry, you can't see me. Hi. So the question about the sea ice, I'm wondering if you think that's related also to the AMOC, because when we found the same coding error in the flux, and also the sea ice albedo. This model is very, very sensitive to the choice of sea ice albedo.
That's right.
In fact, within 1 or 2% change in the sea ice albedo gives you either ice-covered Arctic or ice-free Arctic. But we didn't see such a dramatic improvement in the AMOC when the flux coding error was corrected and the sea ice albedo was corrected. So there's still an issue with the freshwater flux in the North Atlantic. And I was wondering if you had further diagnosed what's going on with the AMOC.
I think we are looking into it. So I think our feeling is improving the sea ice as an implication on the salinity, which in turn affects the AMOC, especially when you run it for longer time. And so you need to improve the sea ice by improving the fluxes, and this can then improve your AMOC as you go along. And you have to run it. Maybe if we have to run it for another few hundred years, then probably we have to see how our AMOC is.
Well, we've run it 400 years, so we
Okay.
don't see that big.
Yeah, so that's a big improvement we see.
Those are really nice. Now, but the one thing that happens when this is so good is people want to work with this. So what is your strategy going ahead in the next few years? I mean, you're going to be on a tight timeline with the
Yeah.
semiprans, and yet there should be some research component where people might want to collaborate. So would you
That's
have like
right,
two
yeah.
versions, and
Yeah.
how does that work out now?
Yeah, so that is something, we have to, said, that we can see. So I put that in the future roadmap on the top. In addition to doing all the CMIP 6 and IP, you have to focus on the basic research. That's very, very important. So how to do that, we can discuss and see how we'll go about mutual interest. But then there are certain commitments which we have to, because this expected from the ministry, we have to deliver that. So this both development and basic research, they have to go hand in hand, and that's very, very important. I think there's
Great, Krishnan. Congratulations to your team.
Thank you.
I think I'm very happy to see the moisture energy improvement. If you connect that to your anticyclonic circulation, have you examined the vertical structure of the diabatic heating the model produces?
No,
Which level it has the maximum heating?
we have to. I think
force
some.
the divergent circulation.
Yeah, because some analysis of the vertical variation of moist static energy, some profiles were made. I don't have it here, but we have to still see that we have not done a very detailed study still. because it was all completed few months back. I mean, just very recently.
Okay, go ahead.
Yes, congratulations, Astro Krishna. Just a question about the people who are using CFS and GFS. One of the biggest problems from the radiative and energy budget is that the atmosphere is almost transparent, and then you have a big bias for downward short-wave radiation. So it is common to many models, but it is also very huge in the normal version of GFS and CFS. So, in fact, when you put the new scheme for convection, it was only for convection. It is not interacting with the radiation code. So my question is that when you have equilibrated that model, did you do something for that big bias for downward short-wave radiation?
Yeah, I mean, see, for example, the aerosols which we are putting, they are interacting with the radiation code. They are interacting with the radiation code.
No, but I'm not speaking about the aerosol. I'm speaking about the clouds.
Okay, so clouds are being computed depending on the humidity in the atmosphere. It's a very simple cloud scheme.
I think Papa can.
Yeah, Partha, you want to answer that?
No, no. See, in the CFS, whatever this convection, convective scheme produces, after the convective precipitations, the remaining moisture, it modifies the atmosphere, then it goes to the microphysics. And the microphysical, the hydrometeor tendencies which are generated, those are used to compute the cloud fraction. And those cloud fractions are subsequently used in radiation to compute the radiation. So what is your question?
My question is that when you look at CFS in these states,
Yes.
you have a very huge bias saying
Yes.
that
Yes.
the atmosphere is almost transparent.
Right.
Okay?
Right.
So, radiation, there is,
so it-
seems that from the radiation,
No, it
point
means
of view,
it
there is
means
no cloud.
no, it means that the interaction is not right. It
Yes.
does not mean that interaction is not there.
No,
Interaction
Agree.
is there.
Agree,
The cloud radius and interaction is not proper.
Agree.
Yeah.
But my
That means-
question is
yeah.
that, so if you start to equilibrate that model to reduce, I mean, what I am saying is that the 5 watt per meter square
Yeah.
in the basic state of the model is coming largely from that.
Probably not
No,
yet.
we see, first of all, yeah, it's a very complex thing. You have to improve the temperature, because outgoing radiation is going to depend on the temperature. So, yeah, we have not really looked at how the cloud has changed. Some analysis we did for the version 1, ESM version 1, but this has, my feeling is a large improvement in this surface temperature has led to improvement in the radiation.
A lot of analysis should be done.
Clouds we have to see.
Any other questions? Then, thank you very much.
Thank
for
you.
This presentation.
So let us thank Professor Insek Kang for sharing the long session and finishing it right in time. I will get back here at 2:15 after lunch.